appreciate the link afterwards. And by the way, are we going out for virtual dinner afterwards as well?
We can discuss that. We can have a virtual conversation about that.
Absolutely.
All right. The jokes just keep on rolling.
Yeah.
Not very good ones, but we'll just keep them going. All right. We'll just wait another couple. Yeah, we'll wait another couple minutes. As usual, people are coming into the lecture hall at the last minute, grabbing their refreshments. Of course, the people who show up late don't see their refreshments because the way Zoom chat works is you don't see what was posted before you sign on. So.
Didn't know that.
So if you're only showing up now, you're missing out on the refreshments that I posted earlier.
But we're not supposed to eat in the lecture hall anyway, so.
That's right. That's right. That's absolutely correct.
Rick and Meg and crew would get mad at us.
Yeah, but I don't think they're here. All right, why don't we get started? Welcome everyone to the CC Colloquium for September 23rd, 2020. We're pleased to have with us Nick Schneider from University of Colorado, and Jim Bell will introduce him in just a minute. Just one reminder note for everybody, there will be a CC community conversation led by the CC leadership team tomorrow. That's tomorrow at noon. There should have been an email circulated about that. You should have noticed that, hopefully. I imagine there'll be yet one more circular about that. So please, if you can, tune into that. It's not the same URL as Colloquium. It's got its own URL. But please try not to miss that. And I'll post some information about that in the chat. And with that, Jim, I'm happy to turn it over to you to introduce our speaker.
All right, thanks, Ariel, and good to virtually see everybody again. Welcome back to CC Colloquium. It's a real pleasure to introduce my colleague Nick Schneider today. I think we're in for a great talk, a real treat. Nick is a professor of astrophysical, planetary, and atmospheric sciences in the Department of Astrophysical and Planetary Sciences at the University of Colorado in Boulder. He's also a faculty research associate in LASP, which is CU's Laboratory for Atmospheric and Space Physics. I think of him as an atmospheric scientist and space physicist and planetary science colleague. He got his PhD in planetary science from University of Arizona down in Tucson. Some of you may have heard of it.
Don't hear any hissing, but.
That's right. And so was, of course, part of that great group that came out of LPL in the 80s. And is very multiple awards and recognition, including a Presidential Young Investigator Award, variety of teaching awards at CU in Boulder, the NASA Exceptional Science Achievement Medal just a couple of years ago. He works in planetary spectroscopy, origin and evolution of planetary atmospheres, magnetospheres. Done a lot of amazing work on the Jupiter and Io system, and is applying his knowledge of space physics to the MAVEN mission, which we'll hear a lot about today. So we'll hear about his work with the imaging UV spectrograph team on MAVEN, but he's also been involved in similar kinds of investigations on the Mars Express orbiter. He was involved in analysis of Voyager data back in the day. Nick and I serve as colleagues on the JANUS imaging team on the JUICE mission, the European Space Agency's JUICE mission to Jupiter and Ganymede. So he's just an incredibly active and prolific researcher, but he has another side of him that I hinted at with the educational awards. He's very, very deeply involved in undergraduate education. We had a great session with Nick and colleagues and a number of CC folks who are working on our undergraduate education and other programs earlier today. And he's an author of a co-author of the textbook called The Cosmic Perspective, which many of you may be familiar with. We use it and do use it in a variety of classes in CC. And Nick and I have enjoyed talking about undergraduate education goals and progress and challenges for many years. So Nick, welcome to CC. It's great to have you visiting with us today. And we're looking forward to hearing all about the great things going on with MAVEN.
Great, thanks an awful lot for the introduction and the invitation. It's great to be with you all. but not as great as when I will get the chance to visit in person. Of all the many places planetary science has done, I've visited so many, but not yet yours, and I look forward to those days in the future. So I'm a Martian now after my early time study of the Jupiter Io system, and I'm going to share a small fraction of the discoveries that our instrument, one instrument on the MAVEN spacecraft, has been able to accomplish. And I realize this is the only slide where I define the acronym I'm going to be using frequently. Imaging Ultraviolet Spectrograph, IUVS, doesn't quite roll off the tongue, but University of Colorado just makes a lot of these, and we have to jumble the letters every time we do a new one of these. So the things that I want to focus on today are some things that were genuine surprises in the scope of our research. First, I'm going to have to give you just sort of the uniform background for everybody on Mars and MAVEN and our instrument. Then these three surprises relate to the comet encounter with Mars, Aurora on Mars, which might have come into this virtual room not knowing exists, and some deep insights into how Mars climate has changed through water loss. And I'm going to end with just a look ahead for MAVEN, who we think has many, many good years in the future. These sound like very disparate topics, but what I want you to do as I go through these is to recognize some of the unifying themes. And Jim has already alluded to planetary atmospheres, space physics. We're also going to be talking about planetary geology, planetary interiors, heliophysics. All these things are essential to understand before you can understand, before you can get the integrated picture of what's happened at Mars. And that's because what we see, and specifically see in the atmosphere, is the reflection of influences from the inside and the outside. And so sometimes simultaneously. And I want you to appreciate those connections and the interdisciplinary nature that is inherent in planetary science. I have the privilege of working with an amazing team, and it's across the board with people at all levels, all institutions, a lot of them at University of Colorado, but many around the world. And as the years have gone by, our team has expanded, especially to other foreign institutions and people outside the team making wonderful use of our data products. And I'm happy to help anybody get involved in that way. So if I can set the stage, many of you will be aware of this background, but let's make sure it works for everybody. These planets shown to scale make it pretty clear Mars is so much smaller that it's going to have profound planetary consequences, 50% farther from the sun than the Earth is. And these conspire to make Mars less habitable nowadays. It's got about 1% of Earth's atmosphere, actually less, primarily carbon dioxide, and temperatures below freezing. And so, but we don't think it was always this way. And this is sort of a schematic of early Mars that might have shown the system like this. Mars would have been warmer inside shortly after formation. It would have had a lot of internal heat giving rise to volcanic eruptions with our cartoon volcanoes spewing out not just lava, but atmospheric gases, giving it a much denser atmosphere, maybe 300 times more than it has nowadays. And that interior is also giving rise to a strong magnetic field that you see right here. This will turn out to be an important player in today's story because it's capable of deflecting, at least back then, solar wind around in the same way that Earth's dipole field does as well. But things changed. Mars cooled off and its volcanoes are virtually extinct, hence the lack of outgassing nowadays. Much of the atmosphere is gone. The interior has cooled off and the magnetic field has disappeared everywhere except for a few special circumstances that we'll talk about. And as a result, the magnetic field interacts far more directly with Mars itself and the atmosphere. And so this really fundamental change has been a mystery and the drive of many missions to Mars. And this really comes home in my mind with this wonderful picture of Jezero crater that I bet is familiar to many in the audience. I've been showing this picture for since it was taken because it's just such a gorgeous manifestation of all the changes that I've talked about. This is the rim of a crater. I think it's about 50 kilometers in diameter that has been pierced by an outflow channel, a water channel that has deposited its sediments in this delta pattern that is readily recognizable here. And the colors overlaid here were obtained from orbital data in the infrared, identifying minerals, and the colors indicate phyllosilicates, clay, mud, muck, whatever. This crater would have been full of water. You'd be walking around in your wellies, and what a great place to look for signs of life. And I could have drawn in the landing ellipse for Perseverance, but this is where it's going, and I couldn't be more excited to know that's the destination. So the puzzle that we're left with is this artist's conception of Mars, perhaps not quite as warm and wet as that, but there are many who think that it was. Where's all that water? If it had several bars of atmosphere, where is it now? There were many initial guesses and early missions designed to measure the abundance. Was it frozen in the poles? Both water and CO2 are frozen there, but not nearly enough. Is it locked underground, permafrost, or formation of carbonates buried deep inside? Not nearly enough. And with this conundrum that was presented as the MAVEN mission was being conceived, nobody liked the idea that the atmosphere hadn't been locked into the planet, because the only alternative is that it had been locked, that the atmosphere had escaped to space. And when the mission was proposed to study this, there were many skeptics, including people on our team, that thought it was not possible for processes leading to atmospheric escape to lose so much atmosphere. So the MAVEN mission was conceived with big questions, and obviously the first thing you need to do is to understand the current atmosphere and what processes are controlling it. Then to measure the escape rate nowadays and related to those controlling processes. And those can be influences from below atmospheric processes, influences from the outside, and both the charged particle and photon influences from the sun. And you combine those to try and understand how the current escape rate can be scaled up through theoretical models, and even scalings measured through the behavior that we see nowadays to find the total loss to space through time. And of course, the big question is the amount of loss that we can determine from our instruments able to explain these incredible changes that have happened in Mars' atmosphere and Mars' climate. What we needed to answer these questions was the MAVEN spacecraft, which you can see is look kind of familiar. There's our 2-meter antenna there, solar panels, and we're just covered in acronyms. Most of these are charged particle instruments, but way down on this boom here are a handful of instruments for observing Mars itself. And looking in on that boom, our instrument, imaging ultraviolet spectrograph, is the only remote sensing instrument on the spacecraft. And these are some particles. This is a mass spectrometer up here, ion measurements here. The important thing here is that we've got gimbals, and this allows this instrument package to be pointed at Mars at the same time the solar panels are pointed at the sun. And also the antenna towards the Earth in general, and therefore allowing us to observe the planet more than 50% of the time, which is really great. There's somebody in the room, the virtual room, that loves diagrams like this. This is for you. we're the 5th spectrograph, ultraviolet spectrograph to go to Mars. And so we have got to do things better, faster, higher resolution, cadence, you name it, and we do. We even have the ability to separate the Lyman alpha line between hydrogen and deuterium. But the main point I want to make with this diagram is to see that we have the means of looking down towards the planet and off to the side as well. And that we're going to make use of that in the observations that I tell you about today. So this is big, it's pretty heavy, uses a fair amount of power, but we needed to do that so that we could accomplish our science goals. All these missions operate, are designed by having a set of science goals. You must remember, or measure a species to this accuracy, at this cadence, etc. And LASP has engineers that do that incredibly well. By the way, those do not look like N95 masks to me, so, but we'll let that pass for now. So the things that makes IUVS special is that we can do imaging spectroscopy. I'll describe how that works, where we basically get a spectrum for every point that we can align our slit with in the instrument. And we have different observing modes, so almost no matter which way we're sharing with other instruments or that the spacecraft is oriented, we're able to take data. And we look at different wavelength ranges, at different resolutions, and really focused on accomplishing different science goals. So the other thing is we're in an unusual orbit. It's a big ellipse, and so we skim down through the atmosphere. That's where our mass spectrometer works. We back off to large distances. That's where particle instruments can measure what's coming from the sun. And this unique orbit gives us this range of viewing geometries for remote sensing. Full suite of particles and fields instruments that has never been flown to Mars in a single package before, all focused on different ways of understanding how atmospheric ingredients might disappear as neutrals, as ions, etc. And what I find particularly satisfying is that we address all kinds of issues across planetary science. And as you'll see today, we were really ready for surprises. NASA required us to be 100% sure that we would measure A, B, and C. And in building an instrument that can do that, we've measured D, E, F on through X, Y, Z, and we'll have to start over with the alphabet, because with a great instrument, the number of new things you can discover that you never proposed to do is substantial. So our two main modes of observing look like this, where we are seeing how the spacecraft looks off to the side, and our slit can be stepped up and down through the atmosphere, measure vertical structure, composition, etc. That's when we're close. When we're far, we can also stare at the planet and look right at it and construct an image out of a bunch of swaths as we sort of paint our slit over the planet. And we can do this over all of our wavelength ranges, basically get it, in both of these cases, we're getting data cubes, where 2 spatial dimensions and 1 spectral dimension for our imaging spectroscopy. So the other diagram that will certainly have some fans in the audience is the spectrum that is so diagnostic of what's happening in the Mars atmosphere. And people have accused us of putting up a model spectrum, but this is just very high signal noise that we've obtained over many, many hours of integration. And while it might look like there's a whole lot of crazy different molecules, like you see here in the mid ultraviolet, a bunch of different atoms down here in the far ultraviolet, most of those are made from the dissociation of carbon dioxide and water, dissociation and ionization, and they end up in excited states and emit like this. Nonetheless, there's some nice surprises that we'll talk about. So not only do we get the spectrum, but in this case, it's a function of altitude, and you can see the scale along the left-hand side, and the main emissions from the byproducts of carbon dioxide are limited in a certain altitude range. But look at this, here's oxygen. It goes off the top of the charts here. It's much more extended. That's in part due to its escape from the planet. This is hydrogen. There's actually virtually no drop in intensity over this altitude range. Hydrogen just goes on and on and on in a way that leads to escape, and I'll emphasize. Many of our spectra do look fundamentally familiar. On the day side, we mainly see these features that you see with our identifications here, mainly telling us that the atmosphere is behaving normally. We can measure how much there is at different altitudes, which gives us temperature, look for seasonal variations, etc. That all goes away on the typical night side, and we see a different gas, nitric oxide. It's not an abundant gas, but it glows with a unique spectrum. It's made from a chemical reaction. And although I'm not talking about it today, it's a really interesting topic in its own right. So I'm going to give you some information overload now, because I know that in your, what is it, the last E is exploration, and everybody's into how are we going to collect the data we need to answer the questions. So I'm going to take you for a ride along on the MAVEN spacecraft. Simulated picture of Mars here. For reference, I told you we can look in two directions, down at the planet or off to the side. And here's where our tiny slit is that lets the light in, and we can move it around to take our spectrum. And the dashboard tells us everything about where we are, where we're looking, etc. For each location of our slit, we take that spectrum. It's actually a two-dimensional spectrum, information along the slit. Here's our friend hydrogen and oxygen. Not much going on here. I think we may be on the night side at this part of the observation. Oh, and we're off the planet as well with the slit. What we're going to see is, now I'm going to animate this for 20 minutes of observations. And you can see the slit wagging up and down. You can see the data changing on the bottom. In the mid-ultraviolet, there are frequent emissions that come from byproducts of carbon dioxide. Here's the hydrogen and oxygen, breakdown of water, also carbon dioxide. For each one of these scans, we're sort of painting a picture, and we can reconstruct where it was looking at all those times. And we've just looked at this one wavelength. I captured that to make this, this image of what the atmosphere looked like as we spun around 90 degrees around the planet. So that gives you a sense of what it's like for us to study the atmosphere. I'm going to do the same thing now for when we're looking at the planet. Mars is smaller because it's at a distance from our apoaps. There's still hydrogen. There's hydrogen everywhere there. And we're going to repeat the same thing. And we're now going to look at the spectrum here. It's going to be reflected sunlight in the mid-ultraviolet. And I'm going to build up an image that you'll see, which actually is the ratio of two points in the spectrum that we see right here. This is sunlight that picks up when we're on the planet. We're painting our image here, and we're seeing the lines, the border between night and day. The right-hand side is sunlit. And we're over the South Pole, as you can see right there. And as we assemble this picture, we're actually getting to see that there's a little bit of structure there. There's some darkness. That's actually ozone, which is absorbing in the Hartley bands in the middle of our spectrum. And we're able to measure that in a single orbit. All right. Then we go off to SLU somewhere else. So I hope this gives you a sense of the data that we can collect in a single orbit. And we've been going for 10,000 orbits in this very rich data set. One of the things we can do is put it together, sort of scale the ultraviolet colors up and see what Mars looked like if we had ultraviolet eyes. And just a few things to point out, since I want to get to our discoveries. We can't see the bottom of Valles Marineris because of Rayleigh scattering. The tops of the volcanoes, some of the biggest volcanoes here, are covered with clouds. But this volcano, Olympus Mons, is so tall that it sticks out of the atmosphere. It's many, many scale heights tall, so that's pretty cool. And we've even constructed a movie from these observations that show how the clouds over the volcanoes grow. By the time it gets to afternoon, they make a band 1,000 kilometers or more. Same way I remember from monsoon days in Arizona, the whole Southwest just clouds over towards the afternoon. All right, so let's talk about these three things that that I've been so fascinated by. First one being Comet Siding Spring. There's a picture from a ground-based observatory. It was a Oort cloud comet, very interesting. Slated to pass 140,000 kilometers from Mars in late 2014. That was weeks after MAVEN was due to arrive. And you can just imagine the discussions that happened, because a comet with the gas and the dust is a nightmare for engineers who want to keep the spacecraft safe. And there was one point where we seriously considered mothballing MAVEN for 2 years, waiting for the next launch opportunity. But instead, the scientists who were all going, yippee, yippee, we get a free comet encounter. We got to take data during the comet flyby, but we actually turned off during closest passage. So the point of this is to set the stage for our observations and ask you a question about your prediction of what happens when a comet passes so close to a planet. And here's our spectrum that maybe you're beginning to recognize with these repetitive features due to the breakdown byproducts of carbon dioxide. So this was hours before closest approach. I guess you have a chat window, and if there's anybody ambitious that wants to predict what change might happen to the spectrum, as soon as I hit the next slide, type it in there, and I'm sure that Ariel will give you some sort of virtual donut or other prize. By the way, shortly before the comet was due to pass by Mars, it was fading, and having gone to this elaborate preparation and hiding the spacecraft behind the planet at the time of closest approach, we wondered if we were going to see anything. So everybody's guesses are in. So we're leaning into our screen, wondering what's it going to be? Will we see anything at all? And kaboom! Anybody guess right? Ionized magnesium was the single brightest emission from the Mars atmosphere as a result of the comet flyby. This is the vaporization, the ablation of meteors in an incredible meteor shower. We detected magnesium plus magnesium, different iron ions. The mass spectrometer not only detected these and other metal species, they even detected the isotopes and confirmed that the isotopic composition of this Oort cloud comet was similar to terrestrial measurements, which is its own incredible story. So from a spectrum like this, you can estimate the amount of material that was deposited. Well, the amount that we observed was about 10 to the 4th mg plus per cubic centimeter. It ended up being global as the planet rotated. Not only did different sides get exposed to the impacts, but the high altitude winds really redistribute things very efficiently. Even so, there's some spatial and temporal structures that we don't fully understand. So an incredible amount of dust was deposited in a very short amount of time. If we know the particle sizes or can estimate them, you can actually figure out the meteor shower rate. This term is the hourly rates of meteors at the zenith. Think about this, thousands to tens of thousands. You go out for the Perseids, you look all night, you see a few dozen. So this would have been truly mind-blowing. One of the many positive outcomes of our detection of that really, really bright signal is the awareness that we could see really, really faint signals. And so Mars is always being bombarded by sporadic meteors not associated with any shower. And so we have a timeline for every day of the mission about how much meteoritic infall has led to these ions present in the atmosphere. The other thing that's important about dust from meteors in the atmosphere makes a solid called meteoric smoke, and it can be the seed particle for mesospheric clouds. To do a little bit of comparison with other meteor showers, the nearest thing that happened to this meteor shower on Mars predates scientific imagery. And so here you see the Leonids of 1833. People thought the world was coming to an end. And the meteor shower rate that we saw at Mars was comparable to this. There may be some dispute saying, oh come on, what about Shoemaker-Levy 9 impacting Mars? I'm going to say that that was not the result of a meteor shower, but the comet itself. And similarly, Chelyabinsk, which was an incredible event. It was largely the burst of a single object as opposed to this global distribution in the form of a meteor shower. So I'm sticking by my claim in my abstract. And what's important about these observations is just this growing awareness that meteor ablation is a planetary process, happens everywhere. Only Earth had had measurements of it previously, and we have added Mars to the list of planets where this can be measured, and even the relative rates of arrival of dust on Mars and Earth can be calculated. And as a last note about this, I'll say that the other importance of these mesospheric clouds is there's great interest in whether or not mesospheric clouds could have had a climate effect on early Mars. As many of you know, there's difficulty in explaining Mars being that much warmer early on. And in addition to magnesium, there would have been an incredible sodium layer that would have been seen here. The sodium layer on Earth is actually illuminated by lasers for telescopic purposes, so that's pretty ingenious. The thing I'll say about, in closing about this discovery is people want to know, would astronauts see this, Martian explorers? And the answer is, oh man, if they could have watched this, it would have been truly mind-blowing. So yes, Matt Damon from The Martian would have seen this. It would have been incredible. All right. Following on this idea of similar processes at Earth and Mars, or maybe they're different, we'll talk about aurora. Everybody thinks about aurora as occurring near the edge of our magnetic field up there in the polar regions, these ovals, where they can precipitate down into the atmosphere. I already talked about how Mars does not have nowadays a dipole field. Its core is apparently no longer convecting. It is not, so there's no dynamo mechanism. What it does have is this weird magnetic field that's locked into lava plains in the southern hemisphere. When these solidified, they locked in the dipole field, which was present at that time. These remnant fields are measurable by spacecraft and mapped, as you can see right here. And so it was logical to say if there is a patchy magnetic field, maybe there will be patchy aurora. And in fact, this is exactly what the SPECAM spacecraft observed. And so it confirmed that mindset about the association of magnetic fields and aurora. Our imaging spectrograph has also seen it. This image here shows some of these little wisps and patches verified by an undergraduate in an honors thesis to be the signature of aurora, excitation of carbon dioxide. And she lined them up on that same map of magnetic fields, and sure enough, they fall right into these lanes. Black and blue is where the field lines connect to space and where particles can precipitate in. And so this is actually a way for us to monitor the interaction between the charged particle environment right around Mars, and especially as it rotates relative to the solar wind. And so it's a great diagnostic for that. That wasn't the only kind of aurora that we saw. There was a solar event of incredible proportions in 2017 directed at Mars. Many spacecraft saw it in their electronics. We saw it in our images. And this bright glow all the way around the edge of Mars is evidence of global aurora. We call it diffuse aurora to give this distinction from the discrete aurora, which is very localized. It's actually far more common and far more widespread than the discrete aurora. This turns out to be, let me freeze this on a single exposure. This turns out to be the straightforward result of solar energetic particles, 100 kiloelectron volts, proceeding unimpeded into the Mars atmosphere. And we sort of did this dope slap saying, why did no one predict this? Why didn't we just, what did you think was going to stop those particles from plowing directly into the atmosphere? Nonetheless, it took going to Mars with the right instrumentation to be able to see this. So the sun has this direct influence right down to 70 kilometers altitude through charged particles. And it's going to cause chemical reactions and energy depositions, and the consequences of that haven't yet been determined. And ironically, this is happening at solar minimum. The sun has been very wimpy. And so we're excited as solar activity increases. So again, we got the Matt Damon question, and the answer is yes. He probably could have seen green and red aurora in the sky during this space weather event as his DNA was being altered. Even the MSL RAD instrument measured this, and so you do not want to watch these aurora. One more phenomenon surprised us for aurora, and this has to do with a curious influence of the solar wind. Mainly protons traveling, here I'll say less energetically, 400 to 800 kilometers per second. As these are penetrating the region on the day side of Mars, they actually steal an electron from the outer layers of the Mars atmosphere, and they become a neutral, and they plow down deep into the atmosphere. And that little electron along for the ride is excited through the collisions and gives off a Lyman alpha photon, another collision, another excitation, another photon. So what's interesting here, the penetrating particle is doing the emission of light, not the background atmosphere. And this process, we think, is probably more common in the solar system. It just hasn't been studied by the right instrumentation. Venus would certainly have this. You need to have a corona of hydrogen, that escaping gas, that escaping cloud, and interaction with the solar wind. By the way, I should have said, this is real data across the bottom, studying just the atmospheric layer in Lyman alpha emission. And when our charged particle instruments measure the influence of incident solar wind particles, we see the creation of this emission. We even see it when we stand off and take our images. This is a day-side aurora, which again is a little counterintuitive, but obvious from the solar wind influence. And a really strange aspect of this is that it depends on the season, and the aurora increase in southern summer when Mars hydrogen corona is enhanced. And I'll talk about how that means that aurora is connected to atmospheric escape. So we now have this rogues gallery of aurora that, quite frankly, most of them were not expected to occur at Mars. And so we have this different view. Because Mars has no magnetic field, a global magnetic field, auroras still occur, but they occur in different places. And the idea that magnetic fields are necessary for aurora is not true. And in fact, I think global magnetic fields should be considered both the cause and the prevention of different kinds of aurora. And so exoplaneteers, please take note. Aurora do occur on unmagnetized planets. Small planets like Mars are abundant, and so they may have aurora. And the implication here is that even substantial aurora for stars and planets close together should not be interpreted as evidence for a magnetic field. All right. The last thing I want to talk about as a science result is water loss and atmospheric escape. Our primary goal was to measure the amount of atmospheric escape and determine whether it was enough to explain climate change. The left image shows a model of how charged particles escape. The right side shows an image of hydrogen actually escaping. This is obtained by our imaging ultraviolet spectrograph. The hydrogen goes as far as we can possibly point. The sum of these two leads to an estimate of the loss of gas has been the dominant process for the changing climate of Mars. That's the conclusion of the MAVEN mission and what we were sent there to do. And to sort of put a point on it, we obtained these images of atomic carbon, atomic oxygen, atomic hydrogen. And this is what happens when hydrogen and carbon dioxide are broken down. They make it to their upper atmosphere where they're able to escape. Hydrogen, being the lightest gas, is able to escape most efficiently. So we got a number for how much is escaping. The mystery was why it was escaping. And we learned that it escapes preferentially in southern summer. We had one instrument that could measure the escape flux of hydrogen and measure these curves here. Southern summer turns out to be when Mars is closest to the sun and the South Pole is also pointed towards the sun. Extra strong seasons. But just because the surface is warmer and the lower atmosphere is warmer doesn't give you an explanation for why there should be enhanced hydrogen escape. What Mike Chaffin, working with our team for many years, has provided evidence for is that the intermediate step is high altitude water. And I'm going to talk that through now. So one of the most important escapes for hydrogen from a planet's atmosphere just has to do with the Maxwellian speed distribution that you see plotted right here. A certain fraction of atoms is going to be above the escape speed marked here. The hotter the atoms, the more can escape. So this is a known process, but it can only happen from the uppermost layers of Mars' atmosphere. So what we see on the left side here was a scenario dating from Jim's and my time from graduate school, where the cold in the upper atmosphere here would cause clouds to form, precipitation, etc. H2O couldn't rise up unless it had been broken down, turned into H2, which could rise up and then be dissociated again. This slow and steady process can only vary on 100-year timescales. We observed it on Mars year timescales. The new scenario is that dusty weather warms the atmosphere, doesn't allow clouds to form. H2O gets high enough up where it can be exposed to sunlight, break down into hydrogen, not only escape, but have a dependence on the season. And in one of the best examples I know of collaboration on climate change on another planet, I'm going to show you results from Mars Climate Sounder, from TGO multiple instruments, and from MAVEN. And so we're going to watch atmospheric escape driven by a dust storm at the bottom. And so here we see the dates where measurements were made. Brown means more dust, so this regional dust storm kicked in and the opacity of dust was measured. Another instrument measured the temperature, and no surprise, the more dark dust you've lofted into the atmosphere, the warmer the temperatures. Same instrument measures ice, and here's the optical depth of ice. It vanishes for that same time period there. We took images. It's a little small, but there's Olympus Mons and the Tharsis volcanoes. Can you see the tiny dots of clouds there? they disappear for a matter of weeks, and they just start to recover at this time here. We're moving up, 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 oops, through the atmosphere. And here's where TGO comes, measuring water vapor. There's a lot low down. When this dust storm has kicked in, here's the water vapor. And it's getting up to 60, 70 kilometers where it is exposed to ultraviolet light. And then IUVS kicks in, and we can actually measure atomic hydrogen that you've seen in the spectrum there. And here it is enhanced in the same time. So on a time scale of weeks, we see dust propagating in effect all the way up through the atmosphere, through to the exosphere, and to the loss of hydrogen. And as a bonus, proton aurora that I've just described to you, look at all those bright sparkles. That's what those dots are, and the lowest parts of the profiles, proton aurora is enhanced. So there it is from the surface to the exosphere, this new paradigm for water loss. And it's may dominate the year's loss of water, and that's a big deal. If escape is not uniform through the year, but happens episodically. And perhaps as important as the geological awareness that some things happen in sort of uniform mode, and sometimes they happen catastrophically. This would be catastrophism in atmospheric loss, at least on a seasonal timescale. So this may have operated for billions of years in this episodic way, hasn't been modeled or tested. All right, so just to wind things up, I see it's time for that. What I really want you to take away from this is these different measurements, quite frankly, none of which were in our original to-do list for Mars, have really expanded our awareness of Mars as it responds to planetary processes. We brought meteor ablation science to another planet, and perhaps a clue towards Mars' early climate through cloud seeding. We've shown that magnetic fields are not necessary for aurora, and in fact, lack of a magnetic field leads to widespread aurora on both the day side and the night side. And there's a new way to think about Mars losing perhaps an ocean's worth of water. What's ahead for MAVEN is to say that we're in an extended mission now. We're getting better coverage, and we're rooting for solar cycle 25 because we really want to see how Mars responds to intense solar activity. Our instrument is performing very well. And so we're hopeful we can keep going for years to come. We've changed our orbit so that we can serve as the internet service provider to the rovers. And so, Jim, as you get back all that data from Perseverance, it's probably coming back through MAVEN, which has the most modern antenna and is really able to transmit a lot of data of yours and excellent science for ours. Our fuel should last into the 2030s.
Thank you, MAVEN.
Briefly, I'll say we're looking for a postdoc. Contact me directly. And this really is my last slide to say, if you haven't seen Mars in the evening sky, make it real. It rises 9 or 10. Look up at it. You'll see that orange point of light. Visualize it as a real planet, not a point of light. Visualize our faithful robot servants there. Thanks a lot for your invitation and your interest. My email is there, and I would love to hear from any of you. And I'm hoping I get some questions from your Colloquium class through the mail too. Thanks.
Thank you, Nick. That was very nice. So as always, folks, you can raise your hand and I'm happy to call on folks. You can also put questions in the Q&A. We have a variety of questions. I'll go for the raised hand first. Jim Lyons, you are able to speak. If you're there.
Yeah, I'm here. Can you hear me, Ari?
Yes.
Yep.
Okay, great.
Just fine.
Nick, that was an absolutely fabulous talk. Thank you so much for that. There's sort of countless questions I can ask, but one of the first questions I would like to ask is a specific one. MAVEN saw, the IUVS saw hydrogen enrichment associated with the delivery of water from the dust tower. Did it also see an oxygen enrichment?
Oh, that's a brilliant question. The oxygen study is underway, and it's trickier. The nice thing about hydrogen is that once it's liberated from the molecule at high altitude, not much happens to it. The same is not true of oxygen. There are a lot of chemical reactions that can scavenge oxygen, and so it's possible for hydrogen to be enhanced, but for the existing reservoir of oxygen at that altitude to hide the signature. But we're looking. Good question.
Okay. Okay, let me let other folks ask questions.
All right. Steve Ruff has a question. Do neutralized solar wind protons reach the surface and penetrate the regolith, acting like neutrons? In other words, could these contribute to neutron-related measurements from other instruments?
This is referring to the proton aurora phenomenon, and I think I have the right diagram here. The question is, how far down do protons go? Or hydrogen atoms as they get converted. And no, they don't reach the surface. And in fact, we see this very discrete layer right here. Let me get you to the right part. This is the diminution at the bottom here is actually the collisional depletion and degradation of the energy of those particles. So I don't think that they affect the measurements at the surface. I've got a couple of follow-ons. There are some people that believe that this process is evidence of addition to hydrogen to Mars, since obviously these are protons coming in. But I did want to make the point that your question as applied to solar energetic particles is correct, that these particles of 100 keV, and we've even seen them up to tens of MeV, do make it down to the surface, and so are therefore a radiation hazard. But the ions, they're easier to stop than electrons.
All right. Jose Iturralde asks, do the loss of gas that was measured off of the Martian atmosphere because of its dust storms, or due to the loss of gas that was measured off of the Martian atmosphere because of dust storms, are there any plans in place to measure spots on Earth with extreme dust storms to measure hydrogen loss in order to verify this hypothesis?
That's a very interesting question, because Earth has the same process of the cold trap, where H2O can't rise too high before it condenses into water or ice. And anything that elevates the temperature of the upper atmosphere allows water vapor to go higher. I think it would take a pretty extreme event for on Earth to warm enough layers of the atmosphere to get that high. On Mars, it's not that far in terms of layers of the atmosphere to get from the surface to what we call the exosphere on the outer layer. But Earth has more than 100 times more atmosphere than Mars. So there's so many grateful things we need to be grateful for about Earth. We have a magnetic field that prevents our atmosphere from being directly stripped away. We have strong gravity, which reduces thermal escape. So I think we are not going to be affected by dust storms and these atmospheric loss processes. But I do know your department has a substantial number of people interested in exoplanets, and we definitely think that this kind of atmospheric loss process could be active on some exoplanets.
Great. Another question. Have you been able to use information from other atmospherically focused orbiters, such as ESA's ExoMars and parts of ISRO's, I'm going to butcher this, Mangalyaan mission, to supplement these exciting discoveries with their observations, or is that not possible because of the nature of your data?
It's definitely possible for these collaborations, and I find that the longer we go on, the deeper our awareness of those collaborations are. The first instrument, or sorry, spacecraft you suggested, ExoMars, is actually another name for trace gas orbiter, which we have used in the studies for this diagram. So absolutely, we're already working with them. We have not been successful yet in collaborating with Mangalyaan, the Indian orbiter. It does have the ability to measure hydrogen, but we haven't been able to confirm our cross calibrations between the two instruments. There's another, well, as you know, there are 3 spacecraft en route right now. One of them is the Emirates Mars mission, also called HOPE, with an instrument from ASU and an ultraviolet instrument from the University of Colorado. And those will definitely lead to some wonderful collaborations. And I actually think there are a lot of ways in which the Emirates Mars mission will do a better job measuring the exospheric hydrogen. But the future is in this kind of international collaboration.
Sam Corville asks, can you tell if hydrogen atoms are preferentially liberated over deuterium atoms?
That's gonna be the talk I give when I get to come in person. So this was a really insightful question, because the shapes of these curves depend not only on how hot your particle is, but how heavy it is. And if I were to draw the same diagram for deuterium, all these curves would shrink over to the left. So by theory, we expect deuterium to escape less, and it was Sam wasn't right? You're exactly right. Deuterium escapes more slowly. I'm telling you in advance of journal submission. Our group at Boston University is working on this, but we have the evidence that the deuterium to hydrogen ratio changes with the season, which is not something anybody expected, especially way up in the upper atmosphere, where people thought these processes equilibrated over hundreds of years. So look for that publication, probably coming out early in 2021. Good question.
All right, so that's a pitch to have you back here again.
Yep.
All right, we got one more question, and it kind of zooms out. It's kind of a bigger picture question from Walid. Basically, I've always wondered if flying asteroids are a danger for space exploration and how we would avoid it.
Everybody remembers science fiction, Star Wars, any number of movies where you have to dodge those asteroids. In truth, they're very far apart. But I have an answer to a different question. What we do have to dodge around Mars is other spacecraft, and there's a whole office called collisional avoidance. So it's so busy around Mars that you may need to shift your orbit to ensure you don't crash into another spacecraft. So that's a bigger hazard than the hazard of asteroids.
All right. Well, on that note, Nick, I think we'll thank you very much again for giving this very nice overview of this mission and the results from it. And thanks very much. And I know you also have a big interest in education and space science education, and that's been really appreciated by some of the community here who met with you. Oh, and I see Jim Lyons, though, has raised his hand again. So I think he has a follow-up question. So we'll just sneak that in because we still do have a minute. Jim, you're allowed to talk.
Okay. So yeah, just a real quick question. Is IUVS used in absorption mode at all? Do you use it for stellar occultations or anything of that sort?
Yes, we do. We can't look at the sun as the ExoMars trace gas orbiter does, but we do have this acrobatic mode where as the spacecraft orbits Mars, different parts of the sky allows stars to rise and set behind the atmosphere. And we've had some really excellent observations there that show atmospheric structure, and even can study the atmosphere on the night side through absorption because it's not glowing in a way that our instrument can see. So,
well, then now that you asked that, now that you asked that, I'm going to follow up because there is another question in the Q&A that I missed. Somebody asked exactly that question Jim just asked, and then said, can it see oxygen isotopes?
Oh, so we can't see oxygen isotopes, although we can measure molecular oxygen. The only isotope we can see is deuterium because the wavelength shift depends on the mass difference, and that's why we have that limitation. But one of your next visitors should be someone from our neutral gas ion mass spectrometer team out of Goddard Space Flight Center, because they've got the isotopes, and argon isotopes have turned out to be a really important tracer of atmospheric loss through the process called sputtering. But I guess all I'm telling you now is that I've given you some results of one instrument on MAVEN, and encourage you to invite more guests.
All right. So on that note, I think we are gonna let you go and let everybody leave the auditorium politely. So thanks everybody for attending, and Nick, again, thank you. And like I said, I know that the people who spoke with you about education really appreciate that conversation. I'm looking forward to having a conversation like that with you later in the week as well.
Like-minded souls fighting the good fight. This was a pleasure. Thanks a lot, everybody.
Nick, thank you so much. We'll stay in touch, okay?
Okay.
All right, take care.
Bye-bye.
Bye.